Welcome to ES 310 Lesson 18. Today we're going to start the second part of the class in which we are looking at rigid bodies instead of particles. And we will start back at the beginning with kinematics. So we're looking at only the motions of those rigid bodies at this point, regardless of the forces acting on them. We're going to focus today on looking at rotational speed because that's what the rigid bodies add to our systems, is the ability to rotate. So we'll look at rotational speeds and accelerations and look at how those are related to linear speeds and accelerations. More information on these topics can be found in Hibbler's Dynamics textbook, Chapter 16, Sections 1 through 4. So as an overview, we have now completed our work on particles. So we looked at the motion of the particles, which was the kinematics, and then we looked at kinetics in three different ways, using Newton's law, using work-energy methods, and using impulse-momentum methods. We're now going to do the same four things with rigid bodies. So today we're going to start in on our motion of rigid bodies. We're going to continue that for a few lessons, and then we will look at equations of motions for rigid bodies, which are Newton's second laws, work-energy methods for rigid bodies, and impulse-momentum methods for rigid bodies. Then we'll look at a few other topics to close out the semester. So, the kinematics of rigid bodies is, first of all, we need to define rigid bodies. So a rigid body is a collection of particles that form a single body. So we can no longer assume things are particles because the shape and their orientation now matter, so that they're rotating in some way. So there's two different types of motion for rigid bodies. There's translation, which is what we've been looking at for particles, right? So in translation, any line in the rigid body stays in the same orientation, but it will move, right? So this vertical line on this body, if it's rectilinear translation, will move along a straight line. If it's curvilinear translation, this vertical line stays vertical, but it moves along a curve. Rotation can be defined about some axis. So we define an axis, and then a point on the body will move in a circle around that axis, and that is rotation. When you combine rotation with translation, you get general planar motion, which is what we'll finish off today with and focus on in the next couple of lessons. So let's take a look at translation. This is what we have been doing, so it should look familiar. This equation, the position equation, is a relative position equation, right? So the position of B is equal to the position of A plus the relative position from A to B. We've been used to seeing this equation written as RBA is equal to RB minus RA, but this is the same idea here. When we take the derivatives of this in order to find the velocity, this term, the relative position from A to B, isn't going to change because the body is not going to deform. So it is 0, the derivative of it is 0. And so you have that the velocity of B is equal to the velocity of A, and you have the acceleration of B is equal to the acceleration of A. So because the body isn't deforming, it's just translating, the velocities and accelerations of every point in the body are the same. Since this is true, that VB is equal to VA and VAB is equal to AA, all of the kinematic equations that we saw previously still apply. And so nothing has changed there. We can still apply all of those various kinematic equations for translation. Now let's take a look at rotation. This is the new aspects that come about when we deal with rigid bodies. So we start by defining a theta, an angular position. To define a theta, we need some reference line that we then define a theta from. So in this case, our reference line is from O to P in the diagram here, and theta then is defined. So in this case, this is our reference line here, relative to some fixed object out here, and theta is defined relative to that reference. d theta is some change in theta, and it's in the direction of d theta is the axis of rotation. So you use your right hand rule again. Your fingers curve in the direction of d theta. Your thumb points upwards, it's a positive rotation. Downwards, it's a negative, but it will always be along the axis of rotation. The angular velocity is defined then as the time derivative of theta, just like the linear velocity was defined as the time derivative of position. So omega, which is your angular velocity, is equal to d theta dt. The angular acceleration is called alpha. Alpha is just the time derivative of omega, so those are equivalent equations to what we've seen before. And we have the combined equivalent equation where alpha times d theta is equal to omega d omega. This is equivalent to a ds is equal to v dv, right? So in all of these equations, all we've done is replace s with theta, v with omega, and a with alpha. And so all of these equations are the same. You just have to remember that the position is being replaced by an angular position, the velocity is being replaced by an angular velocity, and the acceleration is being replaced by an angular acceleration. If you have a constant angular acceleration, we have the constant acceleration equations, again with these substitutions made. So if we know the rotation of a body, we can find information then about the motion of any point in that body. So the relationship between position and angular displacement comes about through r. This is just a geometric definition of an arc length relative to the enclosed angle. That's where this is coming from. So ds is equal to r d theta. Similarly then, v is equal to r omega, and some portion of a is going to equal to r alpha. So, to keep the directions correct, we have to remember this cross product, right? Because we're crossing r and omega in order to find v, and it's omega crossed with r. Is the order, and that order is important. We would only probably use these cross products if we were working in 3D. Most of our motion, we're just going to use omega times r because we're working in one plane. So omega is out of the plane, v and r are within the plane. The acceleration, because we're rotating, things are moving along a curve, we're going to think in terms of normal and tangential components, right? So the tangential component of acceleration, if you think back, was defined as v dot. Well, v dot is time derivative of v. Let's take our definition of v in terms of angular velocity, plug it in. Right, r is not going to change. R is a constant, so r can be factored out, and you have d omega dt, which is defined as alpha. So the tangential acceleration is alpha times r. The normal acceleration, if we remember back to the definition, was v squared over rho. Well, rho in this case is r, the radius of our rotation. V is omega r, so we plug that in, we get omega r squared over r. Divide that out, we get omega squared r. So our total acceleration is the sum of those two parts. And in vector notation with cross products, we get alpha crossed with r for the first term, omega squared, which is not a vector, times r, which is a vector. And there's a minus sign here to incorporate the fact that the normal is pointing towards the center of the circle. So let's take an example of this. This is in old cars, right, that don't have power windows. This is how you would roll up and down the window. So you have a crank that the hand is on here, and you turn that crank, and as you turn that crank, you shift the angle of this S gear, this partial gear, which causes this beam to rotate upwards or downwards depending on which way you're turning, and this one's fixed to a fixed point, so this is going to move the same amount. This just keeps it aligned, right? Adding this one. If this weren't there, this whole thing would rotate, right? So then A and E are going to move up, and that's going to cause the window to move up. All right. So let's see. When A and E, though, A and E are actually moving tangential to this circle, right? Because they're both pinned at here. So the velocity of A and E is sort of at an angle here. And this angle, if we look at the geometry here, the angle in there is the same as the angle down here. All right, so this angle in here is theta. Okay, so now let's take a look here. So we're putting in motion at the top onto this gear, and we're trying to figure out how fast the window goes up and down based on that. So let's take a look at cog C first, which is this little gear here. Cog C has an angular velocity, omega, of 0.5, and it has a radius of 20 millimeters, or 0.02. So the velocity of a point on the outer surface of cog C, right, is going to equal omega times r, which is equal to 0.5 times 0.02, which is equal to 0.01. Alright, so that is the velocity of the point on the outer surface of C. Well, the outer surface of C is meshed with the outer surface of S, this spur gear. So they were going to move together because the gears are locked together. So the velocity of the spur gear, S, right, so the outer point on the outer surface of the spur gear is going to have the same velocity as the cog because they're meshed together. So that's going to equal 0.01. And then we have the radius of the spur gear is equal to 0.5. So the angular speed omega of the spur gear is going to equal V over R, which is 0.01 divided by 0.5, which is 0.02. So this spur gear is moving with an angular velocity of 0.02. Well, this rod is rigidly attached to that spur gear, so this rod is also moving at an angular velocity of 0.02. So this point out here, point A, so we have rod, BA, has an angular velocity of 0.02, and a radius, or length in this case, of 0.2. So the speed of point A is going to equal omega r, which is 0.02 times 0.2, which equals 0.004. And the units would be meters per second. Alright, so that's the speed. The direction of that speed is at this angle, right? Because it's tangential, or it's normal. This is a right angle. It's normal to the radius, or the length of the rod in this case. So then the velocity then of point A, let's write it as a vector, would equal 0.004, and the x part would be the negative sine of theta I hat, and the y part would be positive cosine of theta j hat. And we're told we're looking at the specific theta of 30 degrees. The window moves in the y direction solely, right? Because it's constrained on the side, so it doesn't move side to side. So the velocity of the window is going to equal the y part of VA, which is equal to 0.004 cosine of 30, then equal to 0.0034 meters per second. So what you see then is that we used this V equals omega r over and over and over again in various forms as we work our way through the various gears and shaft systems. And then we recognize that the window is in the y direction, VA is in is normal to the radius direction, so it's in the tangential direction. And so we find the y part of that tangential velocity and find our velocity of the window. So let's take another look at an example here. Here we have a series of gears that are meshed, but what this includes is the kinematic equations that we have been seeing. So we start at point A. We're given alpha of A is equal to 90. So knowing alpha A, we can find the acceleration of a point on the outside edge of A, where it's meshed with B. So the acceleration of A is going to equal alpha A times r. And the acceleration of that point is also going to be equal to the acceleration of the outer point on B, which is equal to alpha B times RB. This is RA. All right, so that will allow us to find alpha B. So from here we get alpha B is equal to, we move the r's over, alpha A, which is known, RA. And so we get alpha B equals alpha A times RA over RB. Now the shaft of B is attached to the shaft of C, right? So from B to C, alpha B is equal to alpha C, right? Because they're on the same shaft, so if B is accelerating with an angular acceleration of alpha C, if B, C will have the same angular acceleration. Then we have a point on the gears where C is meshed with D. So knowing alpha C can give us AC. So AC is equal to alpha C times RC, and that the acceleration of the point on the outer side of C is equal to the acceleration of the point on the outside of D, because they're meshed, so that's AD, which is equal to alpha D RD, and we're looking for the angular velocity information about D. And so if we can find the angular acceleration information about D, we can figure out through kinematics what the velocity is. So solve this for alpha D is equal to alpha C RC over RD, but alpha C is equal to this, right? So this is going to equal alpha A RA RC over RB RD. And all of those are known, so we can plug in all those numbers. We get 90 times RA is 15, so 0.015, times RC is 25, 0.025, divided by RB, 0.05, times RD, 0.075. We plug all those numbers in, and we get that alpha D is equal to 9. So now knowing alpha D, we want to figure out information about angular velocities, it looks like. So it says we start from rest, so omega naught is equal to 0. And we're trying to get to a velocity of 600 RPM, so omega final is 600 revolutions per minute. But we need that in radians per second to keep our units the same. So there are, in 1 minute, there are 60 seconds. And in 1 revolution, there are 2 pi radians. Multiply that out, we get 62.8 radians per second. So we have an initial velocity, omega, angular velocity, a final omega. We have the alpha, the acceleration, equals 9, which is constant, so we can use our constant acceleration equations. We want to determine the time that it takes to do this, and determine the number of revolutions it takes to do this. So if we go back to our kinematic equations, here they are. In the first one, we're looking for time. We know omega, omega naught, and alpha. So we're going to use the first one to find time. Once we know time, we know omega naught, we know time, we know alpha, we can find our angular position, the number of revolutions, in other words. All right, so the first equation was the omega equals omega naught plus alpha t. So that's equal to 0. This is 62.8 plus 9 times t gives us a t equal to 6.98 seconds. And then we use the second equation, which is the theta minus theta naught is equal to omega naught t plus 1/2 alpha t squared. This is 0. So we plug everything in and we get 219 radians. Divide that by 2 pi, you get 34.9 revolutions in order for it to go from 0 to 600 RPM. Now let's take a quick look at absolute rigid body planar motion. In our next lessons, we're going to be looking at relative planar motion. So today we're going to look at absolute. Think back to when we were looking at relative motion, like with our pulley systems and things like that. This is going to parallel that, except now we're incorporating rotation as well. So planar motion involves translation and rotation together. To solve these types of problems, we're going to pick some point on our body. Sometimes that point's given, sometimes we just pick it, and give some information about that point relative to some fixed origin. So that's our position S. Then we have an angle also drawn to a fixed line on our body from a reference, and through the geometry of our body we can relate S to theta. And then we can take time derivatives of this relationship to find velocities, accelerations, angular velocities, and angular accelerations. So this will make more sense through an example. So we have a series of bars here. So there's some motor that pulls this bar around, the first bar, AB, and that causes B to move, which causes C to move, and C will slide along this slot back and forth, depending on what this is doing. So in this case, A and B are equal. So we've got 0.3 for A. So A is equal to 0.3 and B is equal to 0.3. If A and B are equal, then if this angle is theta, this angle is also theta. It's an equilateral triangle. Alright, so our goal then, the position of C is what we're trying to describe. So let's call this distance from our fixed point to C S. And our goal is to relate S to theta. And then we can take derivatives. So to relate S to theta, we look at these triangles. Well, let's split it, right? Those two triangles are the same, right? Because this is 0.3, that's 0.3, that's theta. So S is going to equal 2 times whatever this edge is of one of these triangles. Well, that edge is 0.3 times, it's adjacent to our angle, so cosine of theta. So S is 0.6 cosine theta. That relates S to theta. Now let's take some time derivatives. So we get S dot, which is V, is equal to 0.6, the constant, the time derivative of cosine of theta. Derivative of the cosine is the negative sine of theta, but theta itself is dependent on t, so the inner derivative is theta dot. Then we take another time derivative, S double dot, which is A. We get 0.6 is still a constant. Derivative of the first, so the derivative of negative sine is negative cosine of theta times the inner derivative theta dot times the second theta dot plus 0.6 times negative sine the first times the derivative of the second theta double dot. So now we know all of these things, right? So we have that theta is equal to 30, omega, which is theta dot, is equal to 10, and alpha, which is theta double dot, is equal to 2. So we can plug all of those things into these expressions. We get S is equal to 0.519. S dot is equal to V, which is equal to negative 3. And S double dot is equal to AT, which is equal to negative 52.6. So this is in meters. This is in meters per second, and this is in meters per second squared.